Hello, and welcome to our session about Azure SQL Database Performance Tuning Tips and Tricks. My name is Dimitri Furman. I am a Program Manager on the Azure SQL Database team, and I will be co-presenting the session with my colleague Balmukund Lakhani, who will take us through the second part of the session. Let's take a quick look at the agenda. So first, I would like to talk about resource management in Azure SQL Database, because that's probably one area where it differs the most from the traditional SQL Server deployments. Then we'll take a look at the important case of data loading in Azure SQL. Then we'll talk about some engine features, database engine features and recent improvements that will be relevant to performance tuning in Azure SQL. We'll take a look at performance tuning tools and techniques that you can use. And finally, we'll close off with a look at common performance tweaks you could use. Now, we will be available to answer your questions during the session, so please feel free to type them and we'll be happy to answer them. Okay, so first let's take a look at resource management. And when I talk about resource management, I'm not referring to things like ARM resources in Azure. I'm talking specifically about CPU, memory, storage, IOPS, and so on and so forth. So that's the resources I'm talking about. Now, in Azure SQL Database, there is this concept of a database service objective, or compute size, or pricing tier. This concept is known by many names, and that's basically is an allocation of resources for your database or elastic pool that is set aside and enforced using resource governance. And we'll talk about the implementation of that resource governance next. And then this service objective is given a name, and that's what you probably know, and that's what you're familiar with when you create a database, you pick one of those service objective names. Why do we need this? So in short, the answer is to provide a balanced database as a service. We need to meet our recoverability SLAs, as well as many other SLAs on high availability, disaster recovery, backup. We need it for predictable performance, for multi-tenant fairness, because the service is a multi-tenant service. So, and that's really the mechanism that allows us to provide a very wide range of service objectives, from something very small, such as a basic database in the DTU model with only a quarter of a CPU core and a modest allocation of memory, and then more than 170 service objectives all the way to the largest M-series business critical with 128 cores and almost 4 terabytes of memory. So let's take a quick look at how resource management is implemented. So there are basically three things that form it. Job objects, which is a Windows concept that allows us to set limits on the SQL Server process that runs on a VM. Then there is something called FSRM, which allows us to enforce disk level quotas on how much disk space a process can consume. And then finally, we have resource governor, and that's basically the same kind of technology that's been available in SQL Server for a long time, but it's been modified and extended for cloud. So I'm going to take a closer look at resource governor, right? And by the way, all of those resource management details, particularly the ones about resource governor configuration, as well as some runtime statistics, are available in DMVs. So those are documented. Please take a look, and they're actually very useful when you're troubleshooting any kind of issues related to resources availability or resource usage in Azure SQL. So some core concepts. There is in resource governor, there is this concept of a resource pool, which is an allocation of some resources such as CPU, memory, IOPS, log rates that the workloads can use. Now, on top of the resource pool, there is something known as a workload group, and you can create multiple workload groups in the same resource pool, all using the same pool of resources. So, and there are other things controlled at the workload group level, such as how many workers you could use, what is the max DOP. You can also control IOPS and log rate at the workload group level as well, in addition to controlling it at the resource pool level. So when you connect to a database, your connection is classified into a workload group, right? And depending on where you're connecting from, it will be classified into a user workload group. That's all user connections go there, or for some kind of a system workload that we run for, say, database metrics collection or backup or any of those things. That will be classified into one of the system workload groups. There is also this concept of min, max, and cap. And what this is, a min is a guaranteed reservation of resources. So if, let's say, at the resource pool level, you set a minimum on, say, CPU, you're guaranteed that amount of CPU for that resource pool. A max acts kind of a soft limit. That's how far you can go if there is no resource contention from other workloads, right? And then there is this concept of a cap, and that's a hard limit. For example, if you set a cap on CPU, you cannot really exceed it, right? So all of this is kind of familiar resource governor concepts, familiar if you've used it before, but that's really the technologies that we use, and it's important to kind of refamiliarize yourself with that if you want to take a closer look at performance in Azure SQL. So if we take a look at a single database, right, not an elastic pool, just a single database in Azure SQL, so that's kind of how this looks graphically. So at the bottom in blue you see resource pools, and you have one large user resource pool, that's where your workloads run. And then you have many smaller system resource pools. That's where things that the service itself uses runs, right? And then on top of those resource pools, you have, again, a user workload group and many system workload groups. So in the DMVs that you see on the right, you can actually see those names, and I'll show you in closer detail how to look at that. Now, if you look at an elastic pool, the picture is very similar, except that now, instead of one user workload group, you have many, one per database in the pool, right? And when you configure min and max DTU or min and max vCores per database in a pool, you're basically setting limits on the workload groups in this elastic pool. Okay, let's move on. So our next topic is data loading. That's a very important topic, obviously. So as we said before, all Azure SQL database have some necessary resource limits. And the one that is most relevant for data loading is maximum log rate, right? And again, that's known by several other names, maximum log IO, log write, log throughput. That's basically all the same thing. So, and it depends on the service objectives that you choose, and it can vary very significantly from a few single megabytes per second all the way to 250 megabytes per second on something like M series with many cores. One thing that's important to know is that every Azure SQL database runs in full recovery model. That means everything is logged to the transaction log, and thus the log rate may be higher than what you're used to if you, let's say, you run in traditional SQL Server in bulk logged recovery model or in simple recovery model. So, and we need that to basically provide that balanced database as a service and to provide SLAs, right? So when you choose a service objective, make sure to you choose something that gives you sufficient log rate, right? Because if you don't have sufficient log rate, there are some workarounds, and we'll go over that. But fundamentally, you should choose something that is both acceptable from the price perspective and has sufficiently high log rate for your workloads. So if you're limited by maximum log rate, so there are basically two workarounds. You can use compression, column stores. That's actually very efficient in working around this problem, because the amount of data you log is reduced maybe by a factor of 5 or a factor of 10. Or you can use, if column store is not a fit for your workload, you can use page compression, maybe row compression. So that's one. And the second workaround is to load transient data. And again, that's for transient data specifically, into TempDB or possibly memory optimized table, right? And we'll have a demo to look at this in closer details. Now, one other reason why people sometimes see slower data loading is because they don't load data concurrently, right? So even if you're loading into a single table, depending on the physical design of the table, it may be possible to have multiple streams into the same table. So if you're seeing that your log rate is not maximized, that's possibly because you're just not driving enough load. And if you're loading into a heap, specifying the tab lock hint will let you have concurrent loads into the same table. If you're loading a clustered column store, then you actually should not use the tab lock hint. And then one other way to achieve concurrent loads is to load into multiple partitions and then switch them into the same table, right? Now, just one other point to call out: if you use geo-replication, or if you are on business critical or premium tier and have read scale, so be careful about overloading those replicas, or maybe undersizing those replicas in case of geo-replication, because then your log rate may be throttled simply because a replica cannot keep up with the load you're putting on the primary. Okay, next let's take a look at a demo. So let me start this, and I'll explain what I'm doing here. So basically, I have 4 databases, similar databases, actually identical databases, and I'm loading the same amount of data, 10 million rows, into all 4 of them in parallel. But the way I'm loading it is slightly different with different options. So while this is running, just to quickly show you the script that I executed in all 4 databases. So I created a user, I created some prerequisites for bulk loading from blob storage, because that's what I'm doing. I'm loading from Azure Blob Storage, doing bulk insert. And then I created 4 tables. So this is a heap, just a heap table without any indexes. Then the same table with the same schema, but with a clustered column store index, right? And then the same table created as a global temporary table, right? In this case, there is a couple of prerequisites. One is that to use bulk insert against this global temporary table, I actually have to grant additional permission in tempdb, right? So that's how to do this. And then also set this database scope configuration so that this table is not dropped when all sessions stop using it. So in this way, this table almost acts as a permanent table, even though it's actually a temporary table. So the key point here is that this table is in tempdb, right? And finally, I have a memory optimized table that is created in a business critical database. So the scenario here is that we load some data into the staging tables, and then we have to do some kind of a transformation, aggregation in this case, and load kind of an aggregated version of this data, an abridged version of this data, into a summary table in each database, in the report schema. Okay, so in other words, the amount of data you have to load into the stage table is much more than the amount of data you actually need to have in your database. Okay, so the way this load is done is by using the stored procedure in each database. Let's take a look at the one in the database with the heap table. So basically, every time you execute the stored procedure, it will load one of the 4 chunks of the data in blob storage. So note that we don't just have all data in a single file. It's chunked, and that's what lets me use bulk insert concurrently. So I'm going to run 4 copies of the stored procedure at the same time, and this way I can increase maximize my log rate, as it were, to achieve a faster load. Okay. So at this point, all of those loads should be done, and let's start by taking a look at the heap case. So here we can see that it took 45 seconds. Okay, and that's going to be our baseline, because very commonly people use just heaps as staging tables, so that's the kind of load time we can expect in this particular case. Next, let's look at clustered column store. And in this case, we have 44 seconds, so very similar time. So it doesn't look like clustered column store actually gave us an improvement here, but that time just doesn't tell us the full story, so we'll take a closer look next. Next, let's take a look at heap in tempdb. Okay, and here we have 25 seconds. Okay, so that's a winner so far. And finally, let's take a look at memory optimized. And here we have 39 seconds. Okay, so not too bad, an improvement, but not as good as what we had with heap and tempdb. So let's take a look at resource consumption on those databases as the loads were running. So here we have heap, and let me just zoom in a little bit. And we can see that for most of the time we were actually maxed on log write. So our log rate was throttled in this case. And that really explains why it took a bit longer, because with a heap, the amount of data you have to write a transaction log is probably the largest, and that's why we are getting throttled. Now, if you look at clustered column store, and you'll remember that this took about as much time as the heap. So what we can see is that log rate is actually nowhere near 100%. It's about 30%, right? So even though CPU is much higher, because we have to do compression, we have to compress data as we load it into the database, log rate is much lower. So what this gives us is an opportunity to have more than 4 concurrent streams into the same clustered column store table. So even though it didn't take much less time, if we increased concurrency to say 6 or 8, this would be a better option than loading into a heap. So clustered column storage actually very commonly provides a good improvement in load duration. Next, let's take a look at heap and TempDB, or our global temporary table. And what we can see here is that there is just no log writes at all. Log write is 0, right? And that actually makes perfect sense, because we are not loading data into the database, we are loading it into TempDB. And TempDB does not have the same log rate governance limit. There is still a limit on the total amount of I/O you can do, but the log rate is not there. And it's actually not only that, because we are loading into TempDB, this is actually minimally logged, right? So TempDB is always in simple recovery model. So that's actually a very nice workaround when you have to load some kind of a transient data that you don't need to keep permanently. Now, and in this case, in case of memory optimized, so similar picture, we don't have any log writes, and that's again because this table is not stored on disk at all, it's purely in memory table. So these last two options, heap in TempDB and memory optimized, provide you with very nice workarounds when you have to load some transient data that you don't need to keep, and also when the amount of data that you have to load is relatively small, because in both cases TempDB is a limited resource and memory is a limited resource, so you can't really use this to load any amount of data. But for relatively small loads, those are very nice workarounds. Okay, let's go back to our session. And next, I would like to talk about new database engine features, and I say new in quotes because they're actually not new. They've been added to SQL Server database engine for the last, I don't know, 5 years probably. But the reason I call them new is because if you just migrated to Azure SQL from, say, SQL 2008 or 2012, 2014, any one of those relatively older database engine versions, then you may find that this is now available to you, and it's actually provides a number of very good performance tuning opportunities. So column store indexes, we talked about that, very high compression ratio, faster loads, very fast analytical queries. In-memory OTP, for example, to avoid TempDB contention or for using natively compiled code. A number of auto-tuning options that we have. Specifically, my favorite is this forced last good plan, which can prevent query plan regressions in the middle of the night, for example, and just automatically fix that. Query store, that's probably the most useful feature you can use from the tuning perspective, and we'll have a closer look at that later, as well as several other things. So I'm not going to mention all of them, but the point is, if you've migrated to Azure SQL from an older database, from older SQL Server version, take a look at what's been added in recent years, because those features will most likely make a very good difference performance-wise. Now, specifically, I want to talk about query processing improvements in the query engine. So, And all of those improvements that we do are tied to something called compatibility level, which is set at the database level. So you can see that over the years, going from compatibility level 130 to 140 to 150, in each one of them, we've added a number of query processing improvements. The important thing to realize is that as you change your compatibility level, you also by default change in something called cardinality estimator, right? And as you do that, you may find that for most queries performance is improved, but then you may also find a few where performance regresses. So if that happens, what you should realize is that those two things are actually decoupled. You can control compatibility level and cardinality estimation separately. So you could still go to, say, compatibility level 150 and keep the cardinality estimation at legacy instead of keeping the default. And you can control both of those things either as a database level configurations or as hints. So let's say you may find that a particular query works better with legacy cardinality estimation, and then you can use this option, use hint, force legacy cardinality estimation for that query only. Okay, so next, a quick demo just to show what you can achieve simply by changing the compatibility level to 150, right? Okay, so let me run this. And here I'm using AdventureWorks DW, an old sample database. And what I'm doing here is basically running a simple aggregation query with a fact table and several dimension tables. And I'm running it 3 times. First, I'm running it with compatibility level 140, using this hint at the query level. Then with compatibility level 150. And then finally with compatibility level 150, but here I also add another hint to disallow batch mode. Okay. So this has, and in between each query, I'm using this DMV, DM exec session wait stats to capture waits that were accrued by this session for when the query ran. So let's take a look at the results. First, let's take a look at the timing. So we can see that the first query in compat level 140 took about almost 6 seconds. Second one took much less, 4. And that's simply by changing compatibility level. And that's because we've used batch mode on raw store, a new feature in compatibility level 150. And then finally, when we turned off batch mode, our time kind of got back into the 5 to 6 millisecond range, and you can see that CPU times were similar. So if we look at waits, we can see that we actually didn't wait much. All the wait times are fairly minimal compared to the total duration of the query. However, what's interesting here is to take a look at the waiting tasks. So we can see that we got about 1400 with 140, and then with batch mode, this went down to about 1000, and then it went back to 1400 with 150 in raw mode. So what this tells us is that we are simply waiting less. We have less points in code where we need to wait. So, and that's because with batch mode we are processing data not row by row but batch by batch. So it's just more efficient for that reason. Okay. Moving on, so let's take a look at some performance tuning tools that you can use, and those are all familiar to you. There is really nothing dramatically new here. You can start by using Azure Portal, and we expose some usage metrics. There are some query performance insights, performance recommendations, so that's a quick way to take a look at the overall performance. But if you wanted to do a deeper investigation or tuning, you will probably use other tools such as Query Store, DMV, some kind of monitoring tools, or possibly extended events. Not to mention any kind of performance tuning scripts that you may have. And specific call out I want to make is to SP who is active. which is a stored procedure that lets you see activity in the database in real time as it occurs, and that's very useful to understand what's happening at a point in time. Okay, so in terms of DMVs, so we have many of them. I mentioned a few that are used probably the most commonly. Again, I would like to mention the one that I just use, dmexec session wait stats, because that's very useful in case you have a query running and it's running for a long time and you don't really know why it's slow. So you can use this DMV to filter by the session speed and then see all the waits that the session has accumulated while it was running. And that very often tells you why the query is slow. Is it waiting on storage? Is it waiting on CPU? Is it waiting on parallelism? And so on and so forth. A couple of things to mention about query store in Azure SQL. So by default, we use something called auto capture mode. What it means is that we actually don't capture every query. By default, we omit queries that run just a few times, or queries that complete very fast. Also, the default aggregation interval length is 1 hour, right? So what it means is if you're troubleshooting some kind of a very granular problem that where data changes quickly, you may want to reduce that interval length to something shorter, say 5 minutes or 15 minutes. Also, if your workload is such that it generates many distinct queries and query plans, you may want to increase maximum query store size. By default, it's 1 gigabyte, and that can be increased probably 2 gigabytes safely. Okay. Next, let's take a look at another demo. And this demo is actually something that happened in real life. It's something that one of our customers ran into, and we helped them troubleshoot this. So even though this may look a little bit far-fetched as I show this, this is not a made-up scenario. Okay, so I am going to start a workload. And then I'll basically explain the scenario. So the scenario is that there is this white table with about 50 columns. All of them varchar 30, right? There is a surrogate key. And then we are doing single row inserts into this table. And in our customer scenario, that was some kind of an IoT workload. So trickle inserts, data arriving one message at a time, and that results in, each message results into a single row insert into this table. Okay, and they were finding that it was actually quite slow, much slower than you would expect with just doing regular inserts into a table. Okay, so we can see that this has completed, and if you look at the total duration, we see that it actually took 42 seconds. Now, if you just think through this, we've inserted 5,000 rows, and even for a small database, and this is a 2-core database, inserting 5,000 rows in 42 seconds does sound quite slow. Okay, so so what we can do here is first take a look at extended events. And I have an extended event session that is running, that I've started before starting the workload. And it's capturing data into ring buffer, and it's actually capturing a sample of this data. Just basically one event, because I only need to see one event captured to understand what the problem is here. And when I say one event, one insert into this table. And here we see it. So this is our insert, and we do it with execute SQL. This is the insert statement. You can see the regular columns close, the values close, and then the parameters, right? And if this was a live session, at this point I would be asking everyone to raise their hands if they can spot the problem. And I'm sure I would have seen a few hands raised. Now, you can see if you take a closer look that all the parameter data types are different. So we have 1, we have 15, we have 23, and then if you look at the actual data used, passed to those parameters, you can see that it varies. And that was the case in our customer's scenario, because every parameter that they were passing was of a different length. So what the developers did, they actually declared the parameter length to be the same as the data length. which may sound like a good idea, but in this case, it's actually not, because that means that every time this statement is executed, it needs to be recompiled from scratch, because we cannot reuse a previously cached plan because of parameter data type differences. So in this case, we basically had 5,000 compilations, and compilations is an expensive process. It can take quite a lot of CPU, so that's really the reason why this was slow. Now, another way we could have looked at this is by using this DMV. So DM resource governor workload groups history EX. It's a long name, a mouthful. But that shows us resource utilization by workload group. And remember, I started talking about resource governor in the beginning of the session. That's really where we can see all the workload groups, and most of them are for various internal workloads. But there is this one specifically, user primary group, right, for database ID 11. That's where our user workloads run. That's where this workload ran a few seconds ago. So if we take a closer look at that workload group, we can see that we get quite a lot of data. So you have requests, you have CPU usage, and you can see that there is this delta prefix, and the delta means it's a difference between this snapshot and the previous snapshot, because each row in this DMV represents a snapshot at about 20-second interval, and we can see that this actually gives us quite a lot of data to troubleshoot any kind of resource usage. We can see reads issued, reads throttled, we can see log usage, and so on and so forth, I/O statistics. So I'm going to focus on a few specific columns. So what we can see here is that we had a spike in the number of requests, which is expected, and you can see that the total is about 5,000. That's 5,000 inserts we did. We also see a spike in CPU usage, but what we also see is this spike in query optimizations. Right, and that's really not something I would expect for a single row insert, because the plan should be just cached and reused. But in this case, every single one of those inserts was causing a compilation. So that's our query optimizations that we can see, and that points to the problem. Okay, so let's go ahead and what I didn't show you, and I do want to show that, is how the resources looked during this time. And we need to go to 15 minutes, and let me take a look at log CPU. Well, log was fairly minimal in this case, but CPU was quite high. Okay, and then if you look at waits, we see write log HADR sync commit, which is kind of expected doing inserts on a business critical database, because we have to write to the transaction log on each insert, and then commit this data to all the remote synchronous replicas. What is not expected is this spike in SQL plans. So you can see we started with almost 0, and then we went to almost 1 gigabyte. So again, that's all of those cached plans, 5,000 of them. Okay, let me clear plan cache. Let me restart the extended event session, and now I will run the same workload one more time. Excuse me. But this time I'm running it with this 0 as a parameter, which just changes the behavior of the stored procedure to use fixed length parameters instead of variable parameters according to data lengths. And this has completed, and the time it took now is only 11 seconds. So that's a great improvement. Can we make it faster? Actually, yes, we can. What we can do is do all of this in a transaction. So I'm going to start a transaction, and I'm going to execute the same 5,000 inserts in a transaction, and I have to add a commit at the end to not leave a transaction open. So 5 seconds. Okay, that's actually because we now don't have to incur the latency of commits to transaction log on every insert. Okay? So we are just having that latency once at the end of 5,000 inserts. So now I'm going to go ahead and commit this. Okay. So one thing we haven't looked at is query store. How does query store look for these two workloads? Okay, so I'm going to use this top resource consumer report, and one thing to know about this, and that's probably something you want to do as soon as you open this, is go to this configure button and change a couple of things. By default, it opens and shows you the queries by duration, and that may be what you want to look at, or it may not. So in this case, I want to look at CPU specifically, so I'm going to change it to CPU time. And then, importantly, by default, the time interval it shows you by default is 1 hour, last hour specifically. So I'm going to change it to last 5 minutes, okay? And let's see what this gives us. Now, by default, you see these bars on the left, which kind of graphically show you the top queries. But in our case, I'm going to change this to a grid view, because the grid shows me the actual query text, and it's easier to find the query I'm looking for in this grid view. So here's our query. This is actually our insert, but this is the one that's been fixed. You can see that we have data types all set to 30, right? And we can see that there are 10,000 of them because we ran this workload twice in this fixed configuration. What I would like to do is find the original problematic query. And if I just scroll down, I don't really see this. And that's because by default, we only see the top 25 queries. So I am going to change it to 250. And let's see if I can see it now. Okay, and I still don't see it. And that's probably because my time interval is set to only last 5 minutes, and it's been more than 5 minutes since I ran that original workload. So I'm going to change it to 15 minutes. And let's see if I can find those queries now. And yes, and here they are. So you can see all of these different parameter lengths, right? That's really the problematic queries. And what we do see is that there are many of them. So for each execution of that insert, there is a separate query in query store with a separate plan ID. So like, for example, in this case, it's ends in 638. If I move on to the next one, it ends at 744, and so on and so forth. So even if we just started looking at this in query store, we would have found the problems this way. So basically, we see that in this case, we've used different performance tuning tools and techniques, and all of them could be used to troubleshoot this problem. All right, getting back to our session. And at this point, I will hand it off to Balmukund, who will take us through the rest of the session. Off to you, Balmukund. Thank you.
Thanks, Dimitri. Hello, everyone. This is Balmukund. I work as a program manager with Azure SQL team at Microsoft. And today I'm going to take this journey forward to help you out and understand how to optimize the resource and the performance issue, if you have any, with the Azure SQL database. So whenever you have a performance problem, first you need to check the resource usage. What are the resources which are under pressure? Is it a CPU resource? Is it a log generation which is being throttled? Or are you running out of worker thread? Based on the problem of what you see, the next action will be determined based on the problem what you have. So very first thing you need to do is figure out what the performance problem we are facing. If you are a UI lover, then in that case you may want to go to the Azure Monitor and in the portal look at the various matrices available in the portal itself. If you are a T-SQL fan, in that case you can use DMVs like sysdm db-resource-stats, which is what I'm going to use in my demos as well. You can also look at, so basically you have to look at each resource, what is under contention. And once you identify the resource, you also need to then determine what bottleneck we are having and what is the way to solve the problem if there is a resource bottleneck. So for example, if you have a bottleneck because of the number of workers, in that case you have to find out the way to reduce the worker or a way by which you can get more workers available. So it all depends on what kind of problem we are facing to solve that particular problem. Now, what are the various tools which are available to for end user to fix the performance problem? The very first thing which comes to everyone's mind is the query store, which is one of the very nice and beautiful tool available to figure out whether there is any query which is running slower. You look at the query store and you look at the top resource consuming query. You will look at the query based on the duration, based on the CPU time, and based on what you get, you will start tuning those particular queries to figure out what next step is going to be. You also need to do a weight stats analysis, whether the weight is coming because on the page latch, weight is coming because of temp DB page, or it is a latch contention because of temp DB. Based on what you see there, the next course of action would be determined. Now, let's say you found a query which is running slow. What is the way to tune the query? The way you tune the query would be either by using a tool which is called as Database Tuning Advisor in on-prem world, or you can also use missing index DMV. Missing index DMV is going to tell you if you have any missing index, which can help run this query faster. Sometimes you may have to rewrite the query to have an understanding about the code flow, and then you write the query in a way that the result doesn't change, but the query performs faster. Sometimes there's a problem which is a reverse of it, which means you are utilizing the resources, and in those cases, that the obvious choice would be to scale down your Azure SQL database to save the cost, because you are not having a resource problem, but you are not having a resource contention, but you have extra resource available, and in that case, you may want to scale down the Azure SQL database to save cost. Now, I'm going to show various demos here. The first demo which I'm going to show you is about a situation and demonstrate a situation where there's a log throttling which is happening because of a secondary read replica is under the pressure. So let's jump into the demo. I'm in the portal now, and as you can see, I'm connected to the SQL, and the SQL which I'm interested in is Lakhani SQL. Let's look at the number of databases there. There are 12 databases, and the one which I'm interested in is DPS 2020. Let's go to configure and see the properties of the database. And as you can see, it is a 4 vCode database, and the important part is it has read scale out enabled, which means it has a secondary replica from where we can perform the reads. Now let's connect to the server. Let's verify various things. Let's look at the server name and the updatability, which tells me it is a read only, read write. So that's read only. This is also read only. So I have to make sure that I'm connected to the primary, which means I should not use the app intent read only. So let me remove that and do a connect again. So this connection now should land on primary replica. Yeah, there you go. It's a rewrite, which means it is a primary where I'm going to do the write activity. All right. Now let's back and verify. Yeah, this was read only. So I have one is primary and one is secondary, and that's the file name. Now let's look at the resource stats, which I explained to you earlier. And if you see, it shows us the average CPU, log, and everything available there. And I have a table here, which I'm going to truncate first so that I don't have any data in the table. Let me truncate the table. There you go. And let's first figure out the max of the ID, and it is null because the table is empty. Now, this query is going to tell you the currently executing query. Let's do it on the other side as well. Max verification, that is null, and that's the same query. There's nothing running on any of the replica, the readable replica or primary. And look at the redo queue size, and it is 0 currently. I'm running this query in 10 times by using Go 10. So you will see all values are 0 there, which is good. All right. Now we are going to minimize that, and let's go ahead and insert some rows into the table, and at the same time run some queries on the secondary replica. Sorry. Now let's go ahead to the primary again and look at the currently executing query. And as you can see, there are insert statements which are there, and I use stress tool to run multiple queries, same query from multiple connections. And if I look at the redo queue size on secondary, as you can see, the redo queue size started increasing. So that's the value of the redo queue, 1242, and then increasing to 1600 megabytes. Let's go ahead and run it. Now this is the weight which Dimitri was talking about the logs and rate. So if I go back and look at the documentation, that's the weight which I am seeing, which essentially is the weight coming because secondary replica is not able to keep up, and I am because of the secondary, the primary log rate has been limited. So there are ways explained there to reduce it. One of the way would be to scale up the replica or reduce the load rather. Let's see. We are still having the same thing. And let's look at the redo queue size, and it has further increased to around close to 3000 MB. And before I close the workload, let's look at the CPU usage on the secondary replica. Let's run that query. And if you see the top rows, you can clearly see we are running at 99% CPU on the secondary, which is causing the redo thread not to keep up and causing more redo queue. Now let's look at the redo queue size now after we close the load. And as you would expect, the the redo queue is slowing down, and eventually it will come to 0. So let's run that. 138 meg, 33 meg, and I think that should be it, and we are back to 0 again. So essentially, this demonstration shows that you need to choose the replica size properly if you're running the workload on secondary and if it is an intensive workload. All right, after the demo of read scale replica resource contention, let's jump on to next demo. And next demo is about a feature called as force last good plan, which comes under the family of automatic tuning of Azure SQL database. This is one out of a few which is available in Azure SQL database. Let's jump into the demo right away. All right, we are in the portal with the database wide world importers, which is having 4 cores, as you can see here. Let's verify from the management studio. This is the server name. This is the database name we are working on. And now also verify the SLO, what I showed you in the portal. So it is business critical 4 cores. Let's look at the tuning option, what we have currently set up for this demonstration. And the first option is turned to off, which is a force last good plan is off as of now. Verify that from the portal. To do that, we need to go to the option called as automatic tuning. And as you can see, the first one, force plan, is turned off, forced by user, because I turned it off. Let's run the load. So first initialize environment, and this is the report.cmd, which will basically run a same query from multiple connections, multiple times onto the SQL database. Let's see what is running currently. Look at the logical reads. They are in range of close to between 1000 to 5000 kind of range, and the CPU time is low. Now let's go back and verify from the dashboard. And if I refresh the dashboard, we should see the CPU is close to 67-ish% average, and the batch requests per second are 9. No, let's refresh it again and see the batch requests per second. They're close to 25-ish batch requests per second, which is happening currently. Now let's run a regression query, which is the same query with the different parameter values, which will cause regression in the query plan. Now let's go back, refresh it, and I'm hoping to see the batch request per second. Let's see the in the backend what is happening. So yeah, if you see the logical reads per query has increased, it has come to in a range of 480,000, 639,000 range as opposed to there you go. As you can see, the batch request per second has started dropping down. Let's refresh it one more time to see, and right now it is 22. Yeah, it has come down from 25 to a lower number. Right now, if I look at the graph, it is between 5 to 10. Let's go back, stop the load, because we need to now fix the problem. And to fix the problem, we need to run a script called as autotune.cmd. It has the alter command to change the database property to turn that value on. Let's refresh the portal to verify. And as you can see, the value has turned on for force plan. Let's do the same verification using the T-SQL also. So I go back here, look at the options, and indeed the first one has turned on. Now what it will do for us is something which is interesting to see. Before that, look at the query, the resource stats. We were in the high range of 90s, which was high CPU kind of issue. Let's go to dashboard, verify that there's no load. I stopped it for sure. Let's verify. The batch requests per second have come close to 0, which means I stopped the load. Now let's put the load again. We do the same steps, same query, multiple connections. It is running as of now. We should see the same coming in here. Let's see the currently running query. And the logical read, if you see, it is still in the range of same earlier the good plan, I should say. Let's see. Yeah, that's the good thing which is happening currently. Now let's cause the regression and see whether we get the good plan being forced. So I ran the regression, and then I'm running the same query again to view the currently running request. And as you can see, the logical reads are still hovering between 1000 to 4000. And let's look at the tuning recommendation DMV. And yeah, as we can see, the force last good plan has been applied because the average query cost has changed to a higher number. So this is the command to force the plan. Now let's look at the various values in the DMV in the readable format. So as we can see, the state is verifying. It went to the state because of this reason, and there's a script available if you want. Now let's verify our theory using the dashboard as well. So just refresh the dashboard, and as you can see, the values are still between 20 to 25, sometime going above that as well, which is a good thing. Even did we run regression, nothing happened. Let's change the range to 30 minutes, and you would the last two spikes which you see, the one has become a spike and came down because of regression, and then other sustained. This area is what I'm talking about. And yeah, the first one basically has reduced the batch request per second, and the second one, even if we run the regression, nothing has happened there because of the last good plan being forced here. Just refresh to the default one. Still we are in a good shape, 25. Nothing going wrong even if we did the regression. Yep, verifying. And if we run it little more time, it should go to success state. That it has. Yeah, there you go. It is in success state, which means, and this is the script which I'm talking about, which you can use if you want to force the plan manually. Let's look at the query store. And for this query, there are two plans. If you see on the right hand side, there are two plans which are available for this query, plan ID 3 and 4. Let's see. Yeah, this was the one. And if I look at this one, which is being the one which is the plan which is not good, is basically the plan which has the seek and the lookup. The other one is a good plan for this query, which is being forced here. Let's minimize that. So why this all happened here? Why there's a regression? And that generally is typically a parameter sniffing. And if you see, it is because of skewed value. We have very large value for the ID package type ID number 7. And so the moral of the story is, if you are using Azure SQL DB, make sure this value is turned on. It is going to give benefit to you. Back to the slide again. The next demo which I have is a behavior which is by default in Azure SQL database, which is called as reader doesn't block writer. In typical on-premise world, you might have faced a situation where there's a big update going on, and then because of that big update, users are not able to select the data, and all reports are being blocked. And the typical thing which is done by DBA is kill the update and let select run, those kind of things. Now this demo will demonstrate the behavior of Azure SQL database, how it happens there. Let's jump to the demo. So we are back in the demo environment, and let's first close out all these windows which we used previously. And let's connect to the server. Now we are going to change the database to blocking demo and do a connect. And there we are. That's the database we are going to work on. And what I'm going to do is I'm going to make two connections in the database to demonstrate the blocking behavior, or rather non-blocking behavior. I'm going to, so this is the one which is going to do a insert statement. I put a value of 5. Let's go to other one, and I do a select here, and I get value 1 and 5. Actually, the 5 which you are seeing in the other window was the earlier value, not inserted now. So yeah, you still see 1 and 5. So just to make it clear, we will change the value, and this time we will insert a value. Let's pick up a number. Let's say I'm going to insert value 6. Once I insert 6, and I go to other one, and I'm gonna select, I see 1 and 5 expected. I should have a block, right? Let's do a commit here, and after doing a commit, let's run the select again, and we see 3 values, 1, 5, and 6. Great. This is the Azure SQL DB. Now let's connect to a local instance of SQL which I have on this machine, and I have a similar database there called blocking demo, and exactly same table. Let's run the insert there also, and I'm going to use 7 just to make a differentiation. And if I go to the other query window, let me pop the value, and if I open a new query, do a select and run that query, and as expected, this is blocked and it is executing, right? This is not getting any result back because there's a lock on the table by the insert because of a transaction. Let's do a rollback this time, and notice the executing word there, which means it is being executed once I finish the rollback, and it gives me a result which is empty because there was no record in the table. So that behavior is different, which is what Dimitri said, right? There are a few things which are different. Why it is happening? Because of the read committed snapshot, which is which is off in the local host, which is my local instance of SQL Server. And if I check the same query on Azure SQL database, let's paste it here, and you would notice that, let's see, the value is actually 1, which means the read coverage snapshot is on. And because of that, you are seeing the behavior where readers are not being blocked by writers into the same table. So yeah, that was it. All right, we are back on slide. And with this demonstration, let's move ahead with the last slide of the session. These are the common performance tweaks what we have learned with the various customers implementation. We can classify them into 3: design, config, and operations. In terms of designing, as Dimitri said earlier, compression, table partitioning, in-memory OLTP, those are the things which are going to help you. And in terms of configuration, the max stop value is set to 0 by default. Usually 1 to 8 is the optimal value. And you also need to enable the auto stats creation. You also should use the latest compatibility level, which is what Dimitri showed you earlier. Enable the force last good plan for auto tuning, which is what I demonstrated. You should have the right compute size selected, and then when you connect to the SQL, there are two policies to connect: redirect and proxy. Redirect is the one which you should use in terms of connecting to Azure SQL database. And in terms of operation, what are the top weights, what you are seeing in the system? Find out the top queries, use the query store, tune them, make sure the stats are up to date, because those are the heart of the query optimizer. With the wrong stats, it can make the wrong estimation, and hence a query taking longer time, even though it could have run faster with the right statistics. Have the proper indexes created, drop the unused indexes, and you can also manually force the query, force the plan via the query store, which is what I demonstrated you, where it was forced automatically. You can also force the plan. With this, we are close to the end of the session. We are there for Q&A. Thank you very much for your participation today. I hope you enjoyed the session and learned something new. Me and Dimitri are there to answer the question if you have any. Thank you very much and have a good day ahead.